introduce it. And we introduce it because we're going to use it in the next lesson, okay? The idea of linearization and differentials. Guys, if I asked you to tell me the cube root of 70, give me the cube root of 70. Tell me what it is. What might you do? Give me some problem-solving strategies. Okay. Cube root. Yeah, cube root of 70. So what is the cube root of 70 equal to, right? What would be some strategies? What might you consider doing? Yeah, so like 2 times 2 times 2 is 8. 3 times 3 times 3 is 27. 4 times 4 times 4 is 64. 5 times 5 times 5 is 125, right? So you can at least give me a bound of where it lies, right? It lies somewhere between 4 and 5, right? It lies somewhere in that interval. Everybody agree? All right. Now here's the thing, right? What if I did this? I'm going to come up here for a minute. What if I graphed the cube root of x? Right? What if I graphed the cube root of x and I found a tangent line to it? Look how closely this tangent line follows this curve. Pretty close, right? In fact, when I'm like really close to 70, pretty darn accurate, isn't it? So what if I linearize this graph by finding the equation of this tangent line and then plugging in 70? Now, where might I find the equation of the tangent line at? How about a value that we know? How about the cube root of 64? If we find the cube root of 64's tangent line, and that's this, then the cube root of 70 is pretty darn close, isn't it? Make sense? So let's try it, all right? So I want to know, what is the tangent to the cube root of x at x equals 64? Because that's going to be pretty close. All right, so what is my equation? My equation is the cube root of x. Guys, same as what? Okay. What's my derivative? 1/3 x to the negative 2/3. How could I rewrite that? 1/3 times the cube root of x squared. Good, there's my derivative, right? Okay, so to figure out the equation of that line, that tangent line, I know I'm going to wind up using this. So I'm trying to find it at 64b, right? So I'm going to do y minus, okay, so the cube root of 64 is 4, equals the slope that we're going to find in a minute, times x minus 64. All right, so what is that slope? Well, what am I going to do? I'm going to take 64 and I'm going to plug it into this, right? Because this represents the slope of the tangent to that curve. Cool? All right, so what is y prime at 64? Well, it's 1/3 times the cube root of 64 squared. And now you get to the point, it's like, come on, Picardo, I might as well just type the cube root of 70 in the calculator. Right? This isn't actually that bad. If this was just the cube root of 64, what would it be? It'd be 4. Well, isn't that the same as the cube root of 64 and the cube root of 64. So the 4 and the 4 is going to wind up giving me what? Yeah. I'm going to have 1 over 3 times 16, or 1 over 48. And that's my slope. If I put that in normal form, I'm going to add the 4, right? Okay, and here's, that's all something that I think you guys would be pretty successful with. Okay, here's where I'm going to introduce kind of a new idea. What I'm going to do is I'm going to call this L of x. And what L of x stands for is the linearization of f of x, right? So we linearized f of x, and we did so at x equals 64. Are we okay with that? So the linearization is this. Cool? All right. Now, how is this going to help me solve my problem? Well, what did I create? I created this line, right? So if I want to know the cube root of 70, by linearizing it, I'm going to get an estimate here, aren't I? Of what I would get were I to actually do it, right? So I'm going to now find this value at 70. So I'm going to do the linearization at 70. So in other words, plug 70 in, right? And if we plug 70 in, we get 4 plus 70 minus 4 is 6 over 48. Does that reduce? That's 1/8, right? That's 4 and 1/8. Same as 33/8. So my estimate is 33/8. Now, one more thing. Go back up here. Evan, you see my curve? Is my curve concave up or concave down at the point of tangency? Concave down, right? So is my linearization going to be above or below the curve? Is my linearization going to be above or below? It's above it, right? So is my estimate a little too high or a little too low? A little too high. Why? Because 70 is right here, right? And if this is a point of tangency, it means that the tangent line just touches it once, right? If this is concave down, it's just slightly above the actual curve. Make sense? So because f of x is concave down at x equals 70, my L of x is an overestimate. Actually, I should say L of 70, not L of x. L of 70 is an overestimate, right? Is that cool? So let's actually figure out what happens. So we have 33/8. Let's see how close we were. $4.125. All right, that's our estimate. The cubed root of 70, 4.12129. And we were an overestimate, right? Cool? Estimate the fourth root of 17. Estimate the fourth root of 17. Well, that sounds close to being the fourth root of 16, right? What's the fourth root of 16? 2. So what am I going to do? Well, I'm going to consider a function, the fourth root of x. And I'm going to linearize and find the tangent equation at x equals 16, right? Because 16 is really, really close to 17. And if we know 16, we can get a really, really good estimate, right? Make sense? All right, so my first derivative is this. If I want to make it look pretty, all right, we got that. So let's find the derivative at 16. Ugh. The fourth root of 16 cubed. Guys, remember that when you do these, you can actually do these in any order you want, right? So what is the fourth root of 16? It's 2, and 2 cubed is 8, and 8 times 4 is 32. So this is 1 over 32. All right, so what do I have? I have my slope, and I have a point. That's the point of tangency, right? So the point of tangency is this right here. All right, so my equation is y minus 2 equals 1 over 32 times x minus 16. So I have that. It's my linearized function, right, at that particular point of 16, right? So what do I want to know? I want to know the value at 17. So let's plug in 17. Oh, that's actually kind of nice. You get the door Gould. I get 65 over 32. All right. Here's the problem. Lexi, I want to know if that is a little bit too high or a little bit too low. But I don't know what the curve looks like, do I? Now, how did we make a determination on this one? Well, we knew what the curve looked like. The curve was concave down at the point, right? So my question is, do we know what the original curve looks like? No. But if you take the second derivative, can't you tell me about the concavity? Right? So were I to take the second derivative right here, right? Were I to take the second derivative, it would be negative 3/16 x to the negative 7/4. What did I do, guys? I used this right here, right? I did the power rule, so I just multiplied this and then reduced this by 1. So what does that look like? That looks like negative 3 over 16 times the 4th root of x to the 7. So hang on a minute. What do I want to know? I want to know about the concavity at my point of interest, right? Well, it's 17. What am I going to do? This is going to get to the 7th power. I'm going to take a square root. That'll be a positive number times 16. That'll be a positive number, but this is negative. So I get a negative value, right? Which means that this curve was CC down. So it looks like this, right? Which means that this was an overestimate. It was an overestimate. Want to see how much? 4th root of 17. And 65 over 32. So this should be my overestimate, right? 2.03125. Just a little bit too much, right, babe? Cool? All right. So that's not too bad, right? We're using some linearization at points. What about this? 3.01 to the 5th. What is this equal to? What is this equal to? Well, what's it really close to being equal to? Yeah, so 3.01 to the 5th is about 3 to the 5th, right? Well, do you guys know what 3 to the 5th is? Oh, by the way, hang on. What's the one that I changed? I changed this, right? So do you guys agree that this has to be the variable when I create my function? So it's going to be y equals x to the 5th, right? So that's the function I'm going to use to analyze this, okay? So we know, actually, let's call it f of x equals x to the 5th. So what do we know about this? Well, we know that at 3 to the 5th is equal to 3 times 3 times 3, 27 times 3 is 108, 243. Okay, so I know that. You sure? Okay, good. Positive? Do you guys believe him? Brandon doesn't. So, what do I want to do, guys? Well, do you guys agree that x to the 5th is going to be some increasing function, right? I want to know what the tangent line looks like at what value? At 3, right? Because if I can get the tangent line at 3, then 3.01 will be pretty darn close, won't it? Okay, so I want to know what is the tangent to f of x equals x to the 5th at x equals 3, right? That'll create our linearization. This is a really easy one, isn't it? So what's the derivative? Okay, and what is the value of the derivative at 3? 3 to the 4th is 81. 81 times 5? 405. Very good. Okay, so I have my slope. I have a point. Oh, do I have a point yet? Yeah, down there. Okay, cool. Write my equation. Y minus 243 equals 405 times x minus 3. So what I use right there, guys, I used my point of tangency, and I used my slope at that point, right? All right, so let's make it a linearization model. And where do I want to know? I want to know the linearization at 3.01. Guys, again, like on a calculus test, you're expected to be able to do that math in your head, right? It's 3.01 minus 3. What's that? 0.01, right? So isn't that the same as 4 over 5 over 100? 0.01 is 1/100th, right? And isn't that a mixed number? So if I want to create an improper fraction, I could take 100, multiply it by that, and then add 405 to it. Agreed? I could do that, right? What do I get? I get 24,300 plus 405. 24,000, 20, 28, 30, no, 24,705, right? Over 100? Which is the same as 247.05. I think I did that right. Cool. Did I do that right? Huh? What? Oh, yeah. I got it. You're right. Yeah, I don't know why I did it that way. That makes more sense. I like your way better. Yeah. Okay, so be it. So this is what we think we're going to get for what? 3.01 to the fifth? Oh, by the way, over or underestimate? I don't know. Hang on. What's the second derivative? 20x to the third, right? What happens if I plug 3.01 into this? Is it positive or negative? Positive, right? So that means this is CC up, which means the tangent looks like that, right? So the tangent line is going to be below or above the curve. Below. This is going to be slightly under. Going to be slightly under. 3.01 to the fifth. 3.01 to the fifth. 247.077. We got 247.05. Just a little bit too low. Cool? It's kind of neat, right? Not really. I think it's kind of neat. All right. This one. Approximate this. Guys, what's E? Okay. What's that number raised to the 10th power? It's E times E times E times E times E times 10 times, right? So a really big number, right? We all agree with that? So does this plus 5 really affect much of this? No, right? So here's the way that I would look at this, right? I'm going to say, okay, I want to linearize f of x equals the natural log of x at x equals e to the 10. Now you're going to look at this and say, well, Picardo, I don't know what e to the 10 is. How am I going to get, like this is your x value, fine. How am I ever going to get a y value? Well, guys, what is the natural log of e to the 10. Well, doesn't that allow you to bring that out in front? So that's equal to 10. So we now know f of e to the 10. So that gives me the point of tangency, right? So here's my y value, and here's my x value. So I have my point of tangency. Now I need the slope, right? Now I gotta know the slope of the function. Guys, what's the derivative of natural log?
Natural log.
Nope.
1 over
1 over x. There you go. 1 over x. So what do I want to know? I want to know the value of that at e over 10. Or I'm sorry, e to the 10th. That gives me everything I need to build my tangent equation, doesn't it? I got my slope. I got my point. So my tangent is y minus 10 equals this. Which means my L of x equation is this. All right, so all I want to do now is what? I want to evaluate this at that value, right? Because that value is really, really close to e to the 10. So what do? I plug it in, right? That's kind of cool. What happened in the parentheses? The e to the 10's canceled out. What's left? 10 plus 5 over e to the 10. And this is what I think that's equal to, or pretty darn close. Before we determine pretty darn close, let's figure it out if it's an over or an under. To figure that out, I got to determine concavity at the point, right? So I need my derivative of this now, my second derivative. What's the derivative of 1 over x? Well, 1 over x is x to the negative 1, right? That? What's this guaranteed to be, positive or negative? Definitely negative, right? Definitely negative. So this is going to be CC down. If it's CC down, that means my tangent is a over estimate. So this is going to be an over estimate. Let's see just how much. 10 plus 5 over e to the 10. Okay, that's what I believe will be my overestimate. And what am I looking at? Natural log of e to the 10 plus 5. Natural log. Now, again, it's probably going to have something to do with the number of decimals that are shown. So there's that. And here's that. So which one was the overestimate? This one was, right? Not by very much, but that was the one that we estimated, right? So the linearization is really, really close here. All right, guys, what I just showed you, right, can be simplified. We can actually do it a little bit easier than this, okay? Well, I shouldn't say that. I don't know that it's going to be any easier. What it will be is this. If I asked you guys to take a derivative of this, what would you call it? You could call it y prime. What if I didn't want it written as y prime? What if I wanted it written in differential form? dy over dt. Tell me what that means. T. Isn't it the same as how y changes in response to the way that t changes? Because isn't that what a derivative does? Analyzes change, right? Well, here's what I do. If I was to take the derivative of this for dy dt, what would I get? Well, I would get 6t squared plus 10t minus 3. And would you agree that because dy over dt is a fraction, that I could rewrite it like this? Any reason why I couldn't do that? Seems legit, right? Seems legit. What is this really saying? It's saying the way y changes is the same as the derivative times the way t changes. Okay. What would I call the derivative here? dz over dx. Now you guys are hesitating because you're trying to remember how to do that, but it's a product rule, isn't it? It's a product rule. What's my u? What's my v? What's u prime? 3x squared. What's v prime? Chain rule. Chain rule. 3 times cosine of 3x. Oh my children have grown. All big. That's exactly right. And we know that this is the same as u v prime plus that guy. So I did all that to impressively show you how much you remember about the chain rule and the product rule. But what could I do if I really wanted to? I could really rewrite it like this. I'm going to make it a little nicer. Fair to say? Any reason why I couldn't? Seems legit. Awesome. And what would I call this derivative? dm over dq. Chain rule. Chain rule. What's the derivative of e to the x? E to the x. So it's the what? It's the derivative of the exponent, which is 10q times the derivative of e to the x, which is e to the x. So it's e to the 5q squared plus 1. So what? Take the derivative of the exponent and then leave it alone, right? Inside, outside. But there's no reason why I couldn't write it like this. And so we just reviewed a couple of differentiation techniques that we haven't seen in a little bit. That's cool. Thank you. Okay. So why would I ever stop doing this? You guys don't get it. Anyways, so there are two ways that we could go about doing this problem. Some sort of machine, right? Spherical bearing, right? Ball bearings used in all types of things, right? Rotors, not rotors, that's not the right word. What is it called? The thing inside the, anyways, can't think of what it's called, but you guys know what a ball bearing is, right? Right? It's like yeah, it's a spherical metal object, and you put a whole bunch of them next to one another, and they move nicely with one another, right? If they're perfectly sphere. So here's the deal: in order for these things to work, they can have no greater error than this, right? So if I wanted them to be 2.3 inches in radius, my question is this: if this is the amount of error that's allowed, what is the possible error in the volume of the object itself, right? So watch what we're going to do, B. The volume of a sphere is 4/3 pi r cubed. And B, do you agree that I could graph this? And do you agree that I could graph this and find out the volume at 2.3? And do you agree that if I was to linearize it like we did on the previous page, I could then plug in 2.3 plus this to find an estimate? Seem reasonable, right? And then it'll tell me about what happens with this particular amount of error. Seem okay? Let's do it. So what is V of 2.3? Okay, well, I get that, right? And what is the derivative of volume? Well, it's 4 pi r squared, right? So I just took the derivative of this. And what do I want to know? I want to know the volumes change at 2.3. So I can create that equation of a tangent again. So do I have enough to build my tangent line? I got my slope and I have my point of tangency, right? So what's it going to be? It's going to be y minus this equals the slope times that. Great, Picardo. So that means that L of x equals this. Like, really, dude? Like, I just want a precise answer, Brandon, okay? That's why I'm doing this. So I want to linearize this at 2.3001. Is that okay? No, there shouldn't be.
Oh.
Because I'm adding 1/10, 100th, 1,000th, 10,000th.
Oh.
I'm adding 1/10,000th, 10, 100, 1,000, 10,000. Got it? Guess what? I made the same mistake when I did my answer key. And I couldn't figure out why the heck it was that I wasn't getting the right answer.
No, I thought you were just forgetting a 0 to make it easier. I was like,
No. All right, let's put it in our calculator and see what we get. 4/3 pi. By the way, I'm going to show you an easier way in a minute, okay? There's an easier way. Times 2.3 cubed plus 4 pi 2.3 squared I guess that's okay, doesn't matter, times 2.3001 minus 2.3. I'm going to put multiplication signs in here because I don't want to deal with any issues. How's that look? I plug it in okay? Say again? Here? We'll do it. I don't know. It'll yell at me if I don't do it right anyway. So I get this. 50.9717. Of course, it's probably more like that, right? So I wonder what the actual volume was, right? So the actual volume, if the machine did it perfectly, was 4/3 pi times 2.3 cubed. Four-thirds pi times 2.3 cubed. All right. So my question is this. There's a difference here, right? So the maximum amount of volume that I could be off is going to be what? That minus that, right? That minus that. I can be off by that much volume. That's the maximum amount of volume that I'll be off. Guys, I'm going to go back to something for a minute. Didn't we called this V prime, right? Right? Couldn't I have called it dV/dr? Could I have called it dV/dr? If I called it dV/dr, the derivative would have still been what? 4 pi r squared. Do we agree with that? Okay. Well, could I write it in that form like we did up here? That differential form? Yeah, I would just write it as what? I'd write it like that, wouldn't I? So what did I want to know? Well, I know the R value. What's the R value? 2.3, right? Hang on a second. So make sure of one thing before I say this, before I flub it up, because we're about to get to like the coolest part. Actually, the coolest part's like right here. Okay. Yes, that's what I thought. Guys, DR stands for what? Such a loser. The change in the radius. dV stands for what? The change in the volume. I want to know what is the greatest possible error in the volume. Wouldn't the change in the volume be the difference from the original volume to the new volume? Wouldn't the change in the radius be the what? The amount that I could be off. So check it out. The amount that the volume could be off is the same as 4 pi r squared times 0.0001. Don't believe me? Oh yeah, and we know r, right? And we know r is 2.3. So watch. 4 pi times 2.3 squared times 0.0001 gives me it gives me the amount of change in the volume of the ball bearing. How cool. We're going to use that exclusively tomorrow.